We're going to look at the first part of Chapter 4, which is called Estimating Roots. There is some terminology on the left-hand side here. We've dealt with square roots and cube roots in the past, and now we're going to go up in our index, which is this number. So we've dealt with 2s and 3s here. We're going to now move on to 4s, 5s. For the most part, you may see the odd 6 or 7. So that whole thing is called a radical. This part here is the index. You may have used that word before. This is called the radicand. So that's the part that is under this radical symbol. In the past, you may have called it a square root sign, but it's called a radical symbol. So this is something that you don't necessarily have to have memorized yet, but after you use it enough times, I think you'll become familiar with it. So we're starting off with a review of how to estimate square roots. So this is something that you've done in the past. So it says estimate the value of the square root of 28. So if we're estimating, the idea is we're not using a calculator. We could just evaluate it in a calculator, but for estimating, we're going to try and work through and use some logic here to come up with an answer that's pretty close. So what we would do is we would think about some benchmarks. So for the square root of 28, we know that the perfect square that's really close to it, that's below it, is the square root of 25, and that would give us 5. And the perfect square above 28 would be 36, which would have an answer of 6. So we know that the square root of 28 lies between the square root of 25 and the square root of 36. So we know our final answer is going to be between 5 and 6. And we kind of examine, is 28 closer to 25 or 36? So it's only 3 units away from 25, but it's 8 units away from 36. So we're thinking it's going to be closer to 5, the square root of 28. So it's not super close to 25. It's not like it's the square root of 26. So I would guess somewhere in around 5.2 or 5.3. Maybe you go in the middle. Depends on what they're asking you to do in terms of accuracy, whether it's the 10th or the 100th. So anywhere between 5.2, 5.3 is a good guess. Would probably even accept 5.4 because at least you're acknowledging that you know that it's less than half. Another way that we would have done it would have been the same process but visualizing it on a number line. So you could kind of either use 2 number lines at the same time or just put 2 different labels on the same one. So square root of 25 is 5, square root of 36 is 6, and you've got your halfway point here, and we know that the square root of 28, well, 28 is less than halfway, somewhere in around here, and then just pick a spot on here that you think is close to that. And once again, this is estimating. You could make the argument 5.1 is a bit low because you're thinking it's getting too close to 25, but normally I say as long as you're on the right side of the halfway mark, you've got a pretty good argument. So that's estimating square roots. You could do the same idea with cube roots. You just have to use the perfect cubes as a benchmark or any other index for that matter. All right, so here are some type of questions that we get out of the 4.1 section. So it says evaluate. A lot of this chapter, I believe, should be done without a calculator. So I do not know what the 4th root of 625 is, but I have a very good guess, and then I can check it. So what this 4th root question is asking me, it's saying what number do I multiply by itself 4 times to get 625? I got to fill in that blank here. Well, when you multiply a number by itself and you have that number wrote out 4 times, those numbers get very large very fast. So even if you wanted to just take a guess and say, well, I thought it was 2, which we know it's not 2, but if we were to test it, what happens? So 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16. So that number, went from a 2. We raised it to exponent 4, and we got 16. So 2 exponent 4 is equal to 16. Okay, well, what about 3? Try 3. So 3 times 3 is 9. 9 times 3 is 27. And then 27 times 3 is 81. So if you notice, there's a very large jump from when we could write that as 2 exponent 4. You write this as 3 exponent 4. It's a very large jump to go from 2 exponent 4 to 3 exponent 4. So we know that it's not going to take long to get to 625. But the hint that I'm seeing is that it ends in a 5. So I'm definitely thinking that it's going to be 5. And if you do a check, 5 times 5 is 25, 25 times 5 is 125, and 125 times 5 is 625. So the answer is 5. You're checking it on a calculator, so now it's a 4th root, so your calculator may be different. My calculator is messing up here. So let's see if we can give it a quick fix. We'll hit reset and try again. All right, so I have to go into my math functions here, and I choose this one. It's got a little variable here where my index goes, and I actually have to go ahead of that, put in the index that I want. So I want the 4 to be where that unknown is, and then I have to go after it to put in my radicand, which is this number after it, and I should get 5, which I do. All right, so this one over here looks a little trickier because it's a decimal number. So a couple different strategies you could use, and we're looking at an index of 3 here. So we're asking what number times itself, multiplying it 3 times. So I see 125 here, even though it is 125 thousandths. I like fractions, so my first thought would be that I recognize that as 1/8. You could switch it to 125 thousandths and then divide both by 125, and you would reduce it or simplify it down to 1/8. So this is actually the same as the cube root of 1/8. And I recognize that both of these numbers are perfect cubes. It's a good practice, or it's a good strategy to have a list of perfect square numbers, perfect cube numbers, probably perfect fourths as well that you can reference, but you'll get used to them. But I do know that 2 exponent 3 is 8, and 1 exponent 3 is 1. So a rule that we learned a while ago was that we can write this as the cube root of 1 divided by the cube root of 8. And we know that that is 1 divided by 2, or 1/2. So if we had to write it as a decimal, since it started as a decimal, it would be 0.5, or you could leave it as a fraction of the half. Another way to do it would be to think, use your knowledge of, I saw 125 actually over here when I did 5 times 5 times 5. So if I'm looking at 3 place values beyond the decimal, you're thinking, okay, well, it's like I'm multiplying by 1/10 3 times as well, so you could kind of logic your way back to just checking 0.5. I like the fraction way. Normally, the numbers that they're choosing, because if they're looking for an answer, normally these, if you're not using a calculator, they should end up being rational numbers. So they should work with fractions. Write each number as an equivalent cube root. So this type of question, it's more so the wording that often gets students. So what does this mean? They're asking us to say, okay, 4 is equivalent to the cube root of what? And we got to fill in this blank here. So once you get it set up like that, well, when we evaluate whatever this is in our calculator, we have to get 4. So the inverse operation of taking the cube root is to actually cube something. So if we do 4 times 4 times 4, we will get the number that has to be in there. So the answer is 64 to go in as our radicand. So write each number as an equivalent cube root. So we would say it is equivalent to the cube root of 64. So if somebody writes this, cube root of 64, it's the exact same thing as writing 4. And you could check it in your calculator, find your cube root function, and put in 64. You're going to get 4. Or you could just do 4 times 4 times 4, and you'll get the 64, which proves that this is also going to be true. All right, so now we're going to look at the cube root of 9/10. So it's a little more challenging. It's a decimal number, but the idea is we're still looking for writing it like this, cube root of, and then what number. And because it says it wants to write each number as the equivalent cube root, the whole radical is going to be your answer. So we got to figure out what number goes in there. It's almost like we're undoing a cube root to find out what that number is going to be. So the inverse operation is cubing something. So we're going to cube 9/10, and whatever that number is goes in as our radicand. So you can do it like this if you want to kind of disregard the decimal and use your knowledge of how your place values work. You can do it that way, or you can just say, well, I know that that is 9/10. Oops, 9/10. And if we're cubing it, that numerator and the denominator both have to be cubed. So, well, 10 cubed is going to be 10 times 10 times 10, which is 1,000. And 9 cubed, well, 9 times 9 is 81. And 81 times 9 is going to give us what? So 9 groups of 1 are 9. 9 eighths are 73, but it's actually like, or sorry, 9 eighths are 72, but it's actually like 9 times 80, which is 720. So 10 times bigger than 9 times 8. And then when you add them up, your two partial products, you get 729. So 729 thousandths. So if you're going to write it as a decimal, 729 thousandths. 9 is in the thousandths place value. So if you're going to write it, your answer, your final answer like this, it'd be the cube root of 729 thousandths. You should be able to confirm that with a calculator by saying, clear this. You want to fight again, do you? All right, so 0.9 exponent 3. We'll confirm that that number was right, which it was. And then if you're talking about saying, well, what's your final answer? We want to know, is the cube root of 729 thousandths the exact same thing as saying 9/10? And when we hit enter,